All right, gang, welcome back. We're going to continue learning how to help us make our graphs. And the next thing that we're going to learn is how to use symmetry to help us finish our graphs. Okay, symmetry is when a graph can be split in half and both halves are mirror images of each other. And the presence of symmetry means that you don't have to do a complete graph. If you know that this half is symmetric to this half, you can just mirror the one half to the other. So it's an attempt to save some work. The parabola that we did in the last video or 2 videos ago, I can't remember which, was an example where we had half of the graph and we did plot 2 more points to figure out what this other half of it looked like, but the left half and the right half mirrored each other, and we used that to complete the graph even though we didn't have all the points. There's 3 types of symmetry. The first that we're going to talk about is symmetric about the y-axis. And this particular graph that I'm about to show you is one that is symmetric about the y-axis. And you can see that the left half and the right half mirror each other, and that it's the y-axis that splits it right in half. That's where the mirror ends up being. The next type of symmetry is about the x-axis. And as you can see in the particular diagram that we have there, first of all, it wouldn't be a function if it was symmetric about the x-axis. But the top half and the bottom half match each other, so that's symmetric about the x-axis. And then the last possibility is that it would be symmetric about the origin. All right, and as you can see by that dotted line, if I have one point in that quadrant and I mirror it across the origin, it's just going to follow this line and go right over there. Or I could have a point up here and it gets mapped down to right there. That's what's meant by being symmetric about the origin. Okay, so it's easy to tell if it's symmetric if you have the graph, but what if you don't have the graph? We need some algebraic methods in order to determine whether a graph is symmetric, because again, we're going to use the symmetry to help us graph. All right. It's going to seem like a lot of work as we start this out, but you're going to notice some things over time and really aren't even going to need to do any work to determine whether or not it's symmetric down the road once you become familiar with this. So, to be symmetric about the x-axis, the y-axis, what you need to do is replace all the x's with negative x in the original function, and then simplify it. And if the resulting function is exactly the same as it was at the start, then it will be symmetric about the y-axis. I know it sounds confusing, but you'll understand with this example. Okay, so I have 2 examples here. We're going to do both of them. We'll do the one on the left first. X squared plus 3. You take all the x's and you replace them with negative x. All right. After you do that, simplify the equation. And you notice that what we have at the end is exactly what we started with in the beginning. And since those 2 equations are equivalent, you know that the graph is symmetric about the y-axis. When we try the next example, again, start the same way, replace all the x's with negative x. Simplify what you have. And if you take a look, we have an x squared, yes, but the 2x turned into a negative 2x, so they're not the same. Therefore, that second equation is not symmetric about the y-axis. So to prove the point, I want to take a look at what the graphs look like. Okay, those are the 2 equations that we had. First one was symmetric about the y-axis. Second one was not. As you can see, the y-axis splits the one in the left right in half, However, the vertex of the other one is off-centered, and so it's not symmetric about the y-axis. So part of what you're going to have to do in homework is just do this algebraic test and make the conclusion whether or not it's symmetric about the x-axis, y-axis, or the origin. So let's try another example with the x-axis. In order to determine if it's symmetric about the x-axis, you replace the y with a negative y. And then you simplify. And again, if the equation is equivalent at the end to the one that was at the beginning, then it would be symmetric. All right, so I have an example here, x minus y squared equals 1. I'm only going to do one example here. Like I said, to be symmetric about the x-axis means that it's not actually a function, and we're going to be dealing with functions more than we're going to be dealing with non-functions. Replace the y with a negative y. Simplify what you have. And in this particular case, what it ends up as is exactly what it started out as. So it is symmetric about the x-axis. And in fact, the graph looks like this. All right, so on the one hand, exchange x with negative x, simplify. On the other hand, exchange y with negative y and simplify. So what do you think we're going to do to figure out if it's symmetric about the origin? How about both? Replace all x's with negative x and all y's with negative y. And if the function is equivalent to the original, then it's symmetric about the origin. So as you go through this, it becomes mildly daunting because you got to change all these things. But like I said, you're going to realize some things down the road, and you'll actually be able to determine this without any work. So let's try these two equations. Replace all the x's with negative x. Replace all the y's with negative y. Simplify what you have. And then if we're going to get a comparison between the original function and the last function, we don't want that negative y there. So just take that and multiply everything by a negative 1 to get that equation there. And do they look the same? We got an x squared and a negative x squared. They do not look the same. So that example is not symmetric about the origin. Okay, the next one, replace all the x's with negative x, all the y's with negative y. Simplify. Don't leave it with a negative y, so multiply everything by negative 1. And what you end up with is exactly what you started out with, which means the second equation is symmetric about the origin. Just to verify that this is true, I'm going to show you the two graphs. The first one was not symmetric about the origin. That's what it looks like. Second one was, and that's what it looks like. And so this point here is mirrored over there. A point down here is mirrored up there. Both of those are across the origin. And that is the end of our video here. Adios!